Okay, we're going to go ahead and do some applications of quadratic functions involving maximum and minimum here. So let's take a look at this example. A pool is treated with a chemical to reduce the amount of algae. The amount of algae in the pool t days after treatment can be approximated by this function. A of t is equal to 30t squared minus 300t plus 1200. How many days after treatment will the pool have the least amount of algae? And what is the minimum amount of algae? So actually here we know that this is a quadratic function that opens upward. So we know it's going to look something like that, and therefore it'll have a minimum right here at the vertex. So to find that minimum, all I have to do is use the vertex formula, and we know that B is negative 300 and A is 30. So if I do my minus B over 2 times A, I'll get negative 300 is positive 300, and then 2A be 2 times 30, that's 60. So 300 divided by 60 is 5, so that would give me 5. And that's actually the value where the minimum occurs. That's not the minimum. So the minimum would occur at 5 days, t equal 5 days. To find the minimum, you actually plug 5 back into the function. So if we plug 5 back into this function, we'll get 30 times 5 squared minus 300 times 5 plus 1200, which is equal to 450. So to answer the first question, how many days after treatment will the pool have the least amount of algae? That'd be 5 days. And then if you want to know the amount of algae, that would be 450 units. And actually, if you want to look at the graph of this, I can show you here. Here's the graph of this parabola. And notice that at day 0 after treatment, you have 1,200 units of algae. But then as the number of days increase, the algae drops down to a minimum value of 450. And then, of course, if it keeps increasing, then the algae begins to increase again. And so you would have to probably treat the pool again at this point. So anyway, that's how that works. Okay, so this next example says, suppose the revenue earned on sending parcels is revenue is x times p, where x is the number of parcels sent and p is the price per parcel. Now, a lot of times p would be a constant, but in this case, p is a function. So the price per parcel actually will vary depending on the number sent. So this formula here is the formula that actually determines the price of each parcel. So basically, if you want to just do some little experimenting here, if you send one parcel, then the price would be $3 minus 10 cents for the parcel. If you sent 2 parcels, the price would be $3 minus 20 cents for each parcel, and so forth. So anyway, this varies based on the number of parcels you sent. So what we want to do here is find out how many parcels a customer needs to send to maximize revenue. Well, first of all, we know the formula for revenue is xp, and we know that p is just this function 3 minus 0.1x. And then so if I replace p with 3 minus 0.1x, then I can distribute the x, and x times minus 0.1x would be minus 0.1x squared, and then x times 3 would be 3x. I just wrote it where I wrote the squared term first. So now I have a quadratic function that opens down, therefore we know it has a maximum because the a term is negative. And now if I want to find that maximum, I can just get the vertex. Well, actually I don't need the maximum. I just need to know the x value where the maximum occurs for this problem. So let's find the x value by using our vertex formula minus b over 2a. And since b is 3, we'd have minus 3 over 2 times a, and a is negative 0.1. And then if you grab your calculator, minus 3 divided by 2 times negative 0.1 gives you 15. So we would actually have 15 parcels. And if you graphed this, you would get a a quadratic function, and this point right here, the vertex would actually be where x is 15. Now, it didn't actually ask for the maximum revenue, but if you wanted the maximum revenue, all you'd have to do is plug 15 into this function for x, and then see what you get for the maximum revenue. Here's another example. You're given a formula that represents the position of a toy rocket that's fired. So this is a quadratic function that opens down, and the question we want to answer here is we want to know when the rocket will hit the ground and what the maximum height of the rocket is. Well, the rocket's going to hit the ground when the height equals 0. So all you have to do is just set this s of t, make that 0, and then you'll get that this function equals 0. Now you can solve this using the quadratic formula to solve this quadratic equation using the quadratic formula. So you should know how to use the quadratic formula. The a is -16, the b is 128, the c is 20. So if you remember, the quadratic formula is minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So I'll leave that for you to research if you need to, but I found that it hits the ground at about 8.2 seconds. I had to use a calculator to figure that out. Now, as far as the maximum height, all I have to do is use the vertex formula. So I'm going to calculate the x value, and actually this really should be a t. So that should be a t value. So the t value would be minus b over 2 times a. So it would be minus 128 over 2 times -16. See, because a is -16 and b is 128, and so that's minus b over 2a. And if you calculate that, you'll get 4. So the rocket reaches maximum height at 4 seconds. And then if you want to actually know the maximum height, that's not the maximum height, that's just when it reaches it. If you want to know the maximum height, just plug 4 back into this function, and so you'll get -16 times 4 squared plus 128 times 4 plus 20, and you'll get 276 feet for the actual maximum height. All right, I've got one more here. A dog breeder has 400 feet of fence, and he wants to use all of that 400 feet to create 3 dog runs of equal area by enclosing a rectangular region and placing 2 links across the inside of the enclosure. So basically what I'm doing here is I'm going to put a length here, and then I'm going to put another length here, and I'm going to put, obviously I'm going to put, let me just show you this, I'm going to put a length going this way here and a length going this way here to close it, but then I'm going to put 2 links down the middle. Okay, so what we want to do is find the dimensions that will maximize the area. Well, the area of the entire enclosure would be the length times the width. So let me start over here. So the area would be length times width. So I want to actually maximize, length times width. And so the problem is that's 2 independent variables. So I need a way to eliminate one of these variables. So what I'm going to do is I'm going to just remember that all of these values have to add up to 400. So 4w plus 2l must add up to 400. Well, then I can solve this for l in terms of w. So if I move the 4w over, I get 2l equals minus 4w plus 400, and then divide each term by 2, I get l equals minus 2w plus 200. Then that allows me to replace this l right here, so I can replace the l with minus 2w plus 200, and then I can multiply it by w, and I'll get minus 2w squared plus 200w, and now that's a quadratic function where w is the independent variable, and it opens down, so therefore it has a maximum. So I'm just going to use the vertex formula. B is 200, A is -2. So I'll do minus b, which is minus 200, divided by 2a, and 2a would be 2 times negative 2, which is negative 4. So I have minus 200 divided by negative 4, which is 50. So the width is 50, and now if I want to know the length that's going to maximize the area, I can just plug the width in here. And so minus 2 times 50 is 100, and negative 100. Minus 2 times 50 is negative 100. Add that to 200, and I get 100. So the length is 100. So the dimensions that would maximize the area would be a width of 50 and a length of 100, and that would maximize that area. This last one's really just a hypothetical. It says, what are the dimensions of a rectangle with a fixed perimeter that would maximize area? Well, it turns out that if you had a fixed perimeter, you could make a long, skinny rectangle or kind of a fat, shorter rectangle. But it turns out that if you have fixed dimensions, it turns out that the dimensions that give you the maximum area in a rectangle is simply a square. Now, so if you took, just say you had 100 feet. So if you had 100 feet and you wanted to make a rectangle that had maximum area, then you would just simply make each side of the rectangle be 25 feet. So you do 25 by 25 by 25 by 25. And that's always, in that particular situation, that's always going to give you the maximum areas when you have a square. Now, the question is, though, I'm not going to show it to you mathematically here, but it turns out that if you took that same 100 feet and made a circular enclosure where the distance around the circle was 100 feet, that circle would actually give you more area. Now, it probably wouldn't be very practical if you were trying to make an enclosure, but if you were making a container, then it might make more sense to make a circular base for your container rather than a square base for your container, because that way the container would hold more volume. Just real quick here, let me just remind you of what you have to do to graph quadratic functions. To graph a quadratic function, first of all, you want to find the vertex. So here the vertex, using the vertex formula, you can show would be the point 26. So we would plot the point 26. And then we want to know where it opens. And since A is negative, it opens downward. And we know the maximum is the y value of the vertex, which is that y value. Now, you can always find y-intercepts by letting x be 0. So if you let x be 0, you get the y-intercept of 0, negative 2. Now notice this is the axis, x equal 2, and the y-intercept is 2 units to the left. So there must be another point right here. So you could plot that point, and then you would have those 3 points to use. And then lastly, if you wanted a more accurate picture, you could actually just plug in a value of 1 here and get its y value, which would be 4. And then since you know that point is 1 unit to the left, then you would know there's another point 1 unit to the right of this axis. So that way you would get a couple more points, and you could use those points. So you could use these 5 points, this point, and then these 2 points, and then the vertex, and you could get a pretty good picture. And then finally, let me just remind you that the domain of a quadratic function is all real numbers. And then in this case, since it opens down, the range would be from negative infinity up to the y value of the vertex, which would be 6. And of course, the 6 is included in the range. And that completes the section on quadratic functions.